Okay, let's unpack this. If you're trying to get your head around cutting-edge physics, or maybe you're just deeply curious, you probably bumped into it,
Hmm.
the single most uh, intellectually stubborn scientific question of the last 100 years, the mystery at the heart of quantum mechanics.
It really is the ultimate paradox, isn't it? And our deep dive today is all about Lee Smolin's book, Einstein's Unfinished Revolution. Smolin takes this, well, radical but actually historically grounded view. He argues the deep problems in quantum physics don't mean nature is just fundamentally weird or unknowable.
Uh-huh.
Instead, he says they point to the theory itself being, well, incomplete. And it's been incomplete for about a century now.
Right, so it's not just physics we're talking about. We're jumping straight into a big philosophical fight, really. It defines the whole book. You've got these two camps.
Exactly.
On one side, the anti-realists. They kind of won, historically speaking. Led by Niels Bohr, they basically said, look, the current theory, it's a perfect recipe for calculating what we see in experiments.
But don't ask it to describe objective reality itself.
Yeah, it's just a tool. Then, on the other side, you have the realists. People like Einstein, Schrödinger, and Smolin himself.
And they fundamentally believe that physics has to aim for a complete, accurate picture of objective reality, no matter how strange that reality turns out to be. It's like the anti-realist baker knows the recipe works, gets a great cake,
Gets the outcome.
gets the outcome. But the realist wants to know everything about the flour and sugar before they even get mixed, wants the full story of what is.
And the problem is, that recipe, even though it works incredibly well, shows us things. Behaviors that just completely break our everyday intuition about how the world works.
We should probably jump into those paradoxes, right? Because they really set the stage.
Definitely. The first big puzzle is superposition. This idea that a particle, say an electron, can be in multiple states at the same time. Like spin up and spin down simultaneously.
Until you measure it.
Until the moment you measure it, then poof, it just collapses instantly into one definite state.
And then you've got entanglement, Einstein's spooky action at a distance. Ah, yes, spooky action. Particles get linked, interconnected, no matter how far apart they are. Miles, light years, doesn't matter.
And if you measure the property of one particle,
The state of the other one is instantly determined. Instantly. Which sounds suspiciously like information zipping across faster than light.
which is supposed to be impossible. Okay, and the third one.
Particle-wave duality, the classic. Quantum objects, they act like particles sometimes, waves other times. It depends entirely on how you decide to measure them.
So if you look for its position, it acts like a particle, pinpointed.
Right. But if you measure its momentum, it behaves like a spread-out wave, and this is key. Quantum mechanics tells us you can only ever know half the story perfectly at any one time.
And that half the story idea hits right at the core of determinism, doesn't
Yeah.
it? Classical physics had this dream. Know the position and velocity of everything now, predict the future forever.
The clockwork universe.
Exactly. But QM, with the uncertainty principle, says nope. You can know position precisely or momentum precisely, but never both at the same time. The more you know about one, the fuzzier the other gets.
Which brings us to what's probably the most frustrating puzzle for Smolin and the other realists, the measurement dilemma.
Okay.
The rules of quantum mechanics, the math, it works perfectly for tiny things, atoms, electrons, but those same rules just seem to vanish or change when you get to bigger things, like the detectors we use to measure them or, us.
It feels like there's a seam in reality, a disconnect between the quantum world and our macroscopic world.
Precisely. A gap in our understanding. Physicists talk about the two rules problem. Rule one is the smooth, predictable evolution of a quantum system when it's left alone, governed by the Schrödinger equation, deterministic.
That's the normal state of affairs.
Most of the time, yes.
Yeah.
But then there's rule two. This is the abrupt, random, jump-the-wave function collapse that happens only when a measurement is made. Suddenly, it's probabilistic.
So we have one rule for quantum systems just doing their thing, and another completely different rule for when we look. That seems arbitrary.
It does. And the consequence is that QM is fantastic at predicting statistical averages. If you prepare millions of identical electrons, QM can tell you exactly what percentage will be spin up, like predicting the average height in a crowd.
But it can't tell you about one specific person.
Exactly. It fundamentally fails to explain what happens in a single individual event. It gives you probabilities, but not certainty for this specific electron right now.
And that failure to describe individual reality, that's why the anti-realists, the Copenhagen interpretation led by Bohr, basically won the argument historically.
Pretty much. They said, stop asking QM to describe reality. It's just an algorithm connecting our preparation of a system to the probabilities of measurement outcomes. Bohr's idea of complementarity was crucial here.
Right, complementarity.
He argued science just had to accept using these incompatible pictures, wave or particle, position or momentum, asking about the electron's definite state when you're not measuring it. Bohr said that's a meaningless question.
You can see why Einstein hated that.
Yeah.
It felt like giving up on the whole point of physics, which is to understand what's really going on.
Yeah.
And this philosophical battle, it really boils down to a concept we need to grasp: local realism.
Yeah, that's the bedrock of classical thinking. It's two ideas rolled into one: realism.
Hmm?
Things have definite properties, like position or spin, whether we look at them or not. The moon is there even when no one's looking.
Seems reasonable.
And locality. Influences can't travel faster than the speed of light. What happens here can't instantly affect something way over there.
Also seems reasonable. But entanglement looked like it broke locality.
It certainly looked that way. And the decisive blow came from John Bell in the 1960s with Bell's theorem. He figured out a way to actually test these correlations between entangled particles experimentally.
And the experiments were done.
Oh yes, repeatedly, with increasing precision. And the results are unambiguous. Quantum mechanics violates local realism. The correlations Bell predicted, the ones that assume local realism, are not what we see. The quantum correlations are stronger.
Wow. So the universe at a fundamental level is either not entirely real in the way we think, or it's not local.
That's the stark choice Smolin emphasizes. The experiments force your hand. Either give up realism, accept Bohr's view that QM doesn't describe reality, or give up locality, accept these spooky connections, and find a new theory that explains how nature manages it.
Okay. So if you're like Smolin, and you refuse to give up on realism, on the idea of a real objective world, you need alternatives to standard QM.
Exactly. You need a theory that is realist. And the first, maybe the most intuitive attempt was the pilot wave theory. Louis de Broglie proposed it early on, then David Bohm reinvented it in the 1950s.
How does that work?
Bohm's theory is explicitly realist. It says there's a dual reality. You have actual particles, he called them beebles, which always have definite positions and follow definite paths.
So they're always somewhere specific.
Always. And then there's also a wave function, but it's not the whole story. It's a sort of guiding wave that deterministically pushes the particles around.
Ah, so the wave tells the particle where to go.
Precisely. And what's really neat about pilot wave theory is that it gets rid of Rule 2, the measurement collapse, completely. The wave just evolves smoothly according to Rule 1.
So Schrödinger's cat.
In Bohm's theory, the cat is always either definitely alive or definitely dead. There's no superposition of alive and dead. The particle positions in the cat and the detector are always definite.
And the probabilities. Why do we still see probabilities in experiments if it's deterministic?
That's another elegant part. Bohm argued the probabilities we see aren't fundamental. They just come from our unavoidable ignorance about the exact starting positions of all the particles in the system, including the hidden details of the guiding wave.
Okay, that sounds, well, pretty good. It's realist, deterministic, explains probabilities. Why didn't it take over?
Well, partly history and the dominance of the Copenhagen view, Bohr's view. Von Neumann had also published a flawed proof supposedly ruling out such hidden variable theories like Bohm's, but the real, persistent scientific challenge.
Let me guess. Relativity.
Bingo. Special relativity. Because Bohm's guiding wave has to influence particles instantly, no matter how far apart they are, it requires non-local connections.
Faster than light stuff again.
Faster than light stuff again. And to make that work consistently, the theory seems to need a kind of absolute background time, a preferred frame of reference for the universe.
Wait, why is a preferred frame such a big deal? Doesn't sound too bad.
Oh, it's a huge deal for physics. Einstein's relativity is built on the principle that the laws of physics look identical for all observers moving at constant velocities. There's no special stationary viewpoint. If Bohmian mechanics needs one specific frame where these non-local things happen instantly,
It breaks the symmetry of relativity.
it fundamentally undermines the structure of special relativity, our best theory of space and time, especially at high speeds. That's a massive conflict.
Okay, that conflict makes sense. So pilot wave has a realism advantage, but a relativity problem. What's the next realist option?
The second approach is to say, maybe the collapse, Rule 2, is real. Maybe it's not just about measurement or observation. Maybe it's a genuine physical process happening spontaneously in nature. These are called physical collapse models.
So the wave function just collapses on its own sometimes.
Exactly. The idea is that it's size-dependent. Tiny things like electrons rarely collapse on their own, so they stay quantum. But big things, macroscopic objects, are made of so many particles that they undergo these spontaneous collapses extremely frequently, making them look classical.
It sort of smooths the transition.
It tries to. People like Roger Penrose even suggested gravity might play a role in triggering the collapse, potentially offering a bridge between quantum mechanics and general relativity, our theory of gravity.
That sounds promising. Does it work?
Well, it runs into the same brick wall.
Relativity again.
Relativity again. For the collapse to effectively localize a large object, it generally needs to happen more or less instantaneously across the object's whole wave function, and instantaneously depends on who's looking.
Different observers moving relative to each other would disagree on when the collapse happened.
Precisely. So, like pilot wave theory, these spontaneous collapse models also seem to require a preferred frame, clashing fundamentally with special relativity.
Okay, so we have two realist options, both struggling with relativity. That brings us to the really wild one, right? What Smolin calls magical realism.
Yeah, the many worlds interpretation, or MWI, proposed by Hugh Everett back in the 50s.
How does MWI try to solve the measurement problem?
It takes the most radical step.
Yeah.
It just throws out Rule 2 entirely. It says the wave function never collapses, ever.
It never collapses. So what happens when I measure the electron spin? It was in superposition.
According to MWI, the entire universe, including you, splits. In one branch of reality, you measure spin up. In another, absolutely parallel branch, an identical copy of you measures spin down.
So every quantum choice, every possibility actually happens in its own separate universe.
That's the core idea. The wave function just keeps evolving smoothly, according to Rule 1, branching endlessly to accommodate every possible outcome of every quantum event.
Wow. Okay, that certainly avoids the collapse problem. But Smolin's a realist, and he's not a fan.
Not at all. He finds it deeply problematic as a realist theory. The first major issue is the absence of probabilities. Remember the Born rule? That's the mathematical rule in standard QM that tells us the probability of getting spin up versus spin down.
Yeah, the 50-50 chance, or whatever the specific probability is.
Right. But in MWI, if the wave function never collapses, then both outcomes happen with certainty, probability 1, just in different branches.
Yeah. Where do the probabilities come from? Why do we, in our branch, see results matching the Born rule percentages if everything happens?
Exactly. MWI struggles to convincingly derive the Born rule from its own premise of purely deterministic evolution. Rule 1, if all outcomes are real, why should we experience them with specific frequencies? It sort of solves the measurement problem by ignoring the probability problem, which is arguably just as central to QM.
Okay. What else?
The second big problem is the ambiguity of branching. When and how does the universe split? What defines the branches? Does it happen when the particle hits the detector? When the detector clicks? When a conscious person reads the result?
It seems really fuzzy.
It's fundamentally unclear within the theory. MWI doesn't provide a clear objective mechanism for defining these splits in reality based solely on the wave function evolution.
And I imagine there are philosophical or even ethical issues, too, with infinite copies of yourself.
Smolin touches on that. If there are infinite copies making every possible choice, including terrible ones, what does responsibility even mean? It gets messy fast. So, for Smolin, MWI fails as a coherent, realist picture.
Okay, so let's recap the realist attempts. Pilot wave clashes with relativity. Collapse models clash with relativity. Many worlds has major issues with probabilities and the branching mechanism.
It's a bit of a frustrating picture if you're a realist.
Which leads Smolin to say, maybe we're barking up the wrong tree trying to patch up QM. Maybe we need something completely new, a real revolution.
That's exactly his conclusion. He finds these existing alternatives unconvincing, primarily because they feel like ad hoc fixes for QM's problems, but they don't really connect with the other huge mysteries in physics.
Like quantum gravity.
Exactly, like unifying quantum mechanics with general relativity, finding a theory of everything. Smolin argues you probably can't solve the measurement problem in isolation. The solution likely has to emerge from a deeper, unified theory.
So instead of just modifying QM, he thinks we need to go back to basics, to first principles.
Yes, very much in the spirit of how Einstein developed general relativity. Not by tinkering with Newton's gravity, but by starting from fundamental principles like the equivalence principle. Smolin suggests we need new guiding principles for the next revolution.
What kind of principles is he thinking about?
He emphasizes a few key ideas. One is background independence. The idea that our fundamental theory shouldn't rely on a fixed, pre-existing stage, like a fixed space-time geometry. Space-time itself should emerge from the theory, from the interactions within it.
No fixed background stage, just the actors creating the stage as they go.
Something like that. Another is relational space and time. He argues space isn't fundamental, but emerges from the network of relationships, specifically causal relationships between events.
But time. He treats time differently.
Yes, this is central to his view. He believes time is fundamental, real, and irreversible. This makes him a temporal relationalist. The universe isn't static. Its essence is evolving in time.
So time is the one absolute thing.
In his view, yes. He even talks about the universe being fundamentally made of events, not things. He calls these fundamental events nads, linked by cause and effect. The idea of temporal relationalism is that to become the process of new events happening based on past ones is more fundamental than to be a static state of existence.
It's a radically dynamic picture. The universe has a constantly unfolding sequence of causal events.
It is, and it suggests that even the laws of physics might not be timeless Platonic truths, but could potentially evolve, emerging from the history of these events. It's an attempt to build a framework where quantum mechanics and general relativity might naturally fit together, unified by this fundamental role of time and causality.
So the big takeaway from Smolin is that even with all the quantum weirdness, superposition, entanglement, we don't necessarily have to give up on the idea of a real, understandable, objective reality. The quest isn't over.
Not at all. The fact that we're still wrestling with these deep questions, that physicists like Smolin are pushing for a more complete theory, it shows that core scientific drive, that expectation that nature ultimately should make sense in a concurrent, unified way.
But getting there might force us to question things we currently take for granted. Smolin's ideas about emerging laws, about maybe even the laws of nature not being fixed forever, but evolving based on precedents. That's pretty mind-bending.
It really is. It challenges assumptions that have been part of physics for centuries.
Which leads to a final thought for you, the listener, to chew on. If physics really does need to hit the reset button, to start again from first principles to finally unify everything, what current, absolutely fundamental principle are you willing to bet might not make it through the revolution? Is it locality? Is it the conservation of energy? Or maybe it's that very assumption that the laws themselves are eternal and unchanging. What might have to give?